Welcome to our next session, where Yuri Winch-Ackerman will give his talk on leveraging oneAPI for industry application, a deep dive focusing on predictive maintenance context. Over to you, Yuri.
Hi, everyone. Thanks, Ben, for the introduction. Thanks, everyone, for attending this session. Really happy to be here with you guys for the next 45 minutes to approach this topic that I've separated for this event, which is on leveraging oneAPI for industrial applications. And moreover, we are going to do some deep dive on the context of predictive maintenance. So yeah, just getting into business here. So as an introduction, I want to firstly cover some of the agenda for this talk. So before we reach into a final conclusion, I've separated 3 sections for the talk. So the first being oneAPI basics. So I'm briefly gonna run through the basic concepts on oneAPI and the frameworks to set a common ground for everyone here, because maybe not everyone knows all the specs and the things that we're going to mention in the final topics. So yeah, after this oneAPI covering, I'm going to go through some predictive maintenance topics on this, covering especially the use case of a specific problem in the industry. And next is going to be some hands-on material. So we're going to run through and go through some coding briefly and to see how oneAPI runs on a real scenario. So yeah, going into our presentation here itself. So talking about the UXL Foundation, for people that are not too familiar with, it's an initiative where it's under the umbrella of the Linux Foundation, and this foundation is dedicated to especially driving open accelerated compute and enhancing cross-platform performance across the industry. UXL brings together a community of technology leaders, developers, to collaborate on open source projects to advance acceleration technologies especially. So its goal is to simplify the development of high performance applications by promoting standards across different hardware architectures. And why is this so important nowadays? In today's evolving tech landscape, there's a growing need for applications to perform efficiently across different platforms without the overhead of rewriting code for each one of the possible architectures out there. So the foundation addresses this by fostering this open ecosystem and paving a way for a more unified and efficient future in accelerated computing. So next step, I think it is of good form to introduce myself here. So what I did in my as a background, I have aerospace engineering and data science as my studies background. I've done research with NASA, Innovative Advanced Concepts, also with MIT Genesis, which is called LIFT nowadays. And then I've worked with some data consulting in a French company, also in manufacturing research, and with my team, we've spinned off a project in the manufacturing topic to a degree of a startup idea. We have been incubated in Microsoft Founders Hub, also RVTH Innovation, and now Intel Liftoff. I'm also ambassador for Intel's oneAPI, so it's a pretty good topic for me. So I'm really driven for this. So yeah, just let's cut to the chase and get into business. So talking about oneAPI, I'm just going to do a brief overview here on the initiative. So let's begin by addressing the motivation behind oneAPI. The high demand for acceleration in high performance computing and AI requires multiple architectures, so CPU, GPUs, FPGAs, and other accelerators, XPUs. And many data intensive workloads perform best when they are deployed across a mix of those. And in fact, there's a study that says that nearly 48% of the developers are now targeting heterogeneous systems that use more than one, at least more than one type of processor. However, programming for different architectures often means using unique languages, tools, and libraries. And this increases a lot of the complexity and limits the code we use, making it challenging to fully leverage the multi-architecture systems and maintain code efficiently. So developers are frequently confined to vendor-specific ecosystems, which can restrict somehow the innovation and increase the development time. oneAPI, in a way, provides developers the freedom to choose their hardware by offering a direct programming model that targets multiple devices. And the powerful oneAPI libraries accelerate functions like math operations, neural networks, ensuring high performance. Especially Cycle has proven performance portability across devices from various vendors, including Intel, AMD, and NVIDIA. And this means developers don't have to write different code for each platform, boosting productivity and reducing the time to market. This commitment to focus on promoting the open programming that frees developers from constraints of proprietary software. By embracing the oneAPI programming model, we join forces with others to drive a vendor-neutral software ecosystem for accelerators. And I think this is a pretty big topic, a pretty big point for me. It is a flag that I like to raise. This collective effort to is a proof that broader industry seeks an open alternative to proprietary platforms like CUDA. For example, there is a growing movement to ensure high performance application code, not locked to specific hardware such NVIDIA GPUs, for example. So here we can discuss what I've just mentioned, Cycle, and the direct programming language of oneAPI, Cycle. It's a object-oriented parallel programming, and it's designed to run on multiple compute devices, as I've mentioned. Some developers are often concerned about performance loss when switching. However, benchmarks show here that migrating workloads achieve comparable and sometimes higher performance on NVIDIA devices. And those tests here that we can see on the graph are on a NVIDIA A100, and the system across 10 workloads demonstrate Cycle's high performance. Additionally, Cycle is effective on architectures like Intel, AMD, RISC-V, ARM, PowerVR, and etc. So also tools like Cyclematic simplify the porting code from CUDA to Cycle, so enhancing the development efficiency on this migration. The software tools powered by oneAPI provide a flexible software stack here. So the oneAPI base toolkit, especially that we see here on the bottom, includes C++ with Cycle, some compilers, libraries, frameworks, and it works. I think it's pretty popular because it also works on some libraries, important libraries like TensorFlow and PyTorch. On today's data-centric workloads, the demand a really diverse type of hardware. So this introduces the complexity, and the space toolkit simplifies this, offering some standards. So it provides all the essentials to build and deploy high performance applications. The toolkit includes advanced compilers, libraries, and also the tools for analysis. One really cool feature, as one tool, is the vTune profiler, which analyzes some hotspots to optimize code efficiency. Also, we have like advisor that helps you determine the optimal mix of computing resources, offering like advice on threading, multi-core usage, and GPU offloading to maximize the performance, which are really cool tools that can be used in this scenario. Now we go to our next session, where the idea is to cover the basic principles of predictive maintenance, how important it is to the industry itself, and how we have seen a big spike in the concern about implementing controlled environments for predictive maintenance. Yeah, predictive maintenance is really essential, and the industries nowadays to minimize a lot of the downtime, reduce costs, and extend the lifespan of equipments by anticipating the failures before they happen. So to implement the predictive maintenance, I've listed some 4 fundamental steps here, and starting with establishing the baselines. So the idea is to collect historical data to understand the normal operating conditions of the machinery. This baseline helps in identifying some deviations that may indicate potential issues in the future. So the second step is to install the IoT devices. So we basically equip the machines with sensors to monitor the parameters like the temperature, vibration, and the pressure in real time. These devices, they gather the critical data for the analysis that we are going to do, and also using oneAPI in this case. So here's where we see the application that we are going to go through. The third step is to connect the devices to the software. So integrate the IoT devices with platforms that can process, analyze, as I said, with oneAPI empowering the computing, and using advanced analytics and machine learning algorithms. And the last step is to use those insights to schedule maintenance proactively and addressing issues before they lead to equipment failure. We can dive now into a specific use case that I wanted to bring here. So this use case in particular is the one that I've been dealing in the last, let's say, 2 years. Basically in the industrial manufacturing, maintaining the sharpness and integrity of the cutting edge of the cutting tools is essential for the product quality and operational efficiency and overall. So traditionally, the toolware is assessed with microscopes or visual inspections, which are often time-consuming, and they rely heavily on the inspector's experience. These methods, they usually require downtime in production to assess the wear on the tools, and it leads to costs at the end. So without monitoring, tool failures can cause defective products that need to be scrapped. Unscheduled maintenance also happens. One cool thing, one fun fact is that many of the companies have been using, many of the companies dealing with cutting tools, especially developing research, they have been using prisoners to do this type of job, especially because of the repetitive procedure in a microscope to reduce the costs of the labor costs. So yeah, it has been a big topic in the industry right now. I've brought some data survey here that we've collected from market players, and it shows that in many experience many of them experienced the unexpected tool failures, and to cope with that, they used scheduled maintenance of periodic inspections metrics like surface finish quality, dimensional accuracy, and vibrational levels. But many of them don't have a automated solution for that. Seeing how cutting tools where progresses here on the left graph. So it is a pretty common structure of the progressing points of the wear. And on the right, we can see the indicative failure modes like flank wear, chipping, and built-in edges that are common in the industry. So understanding that the predictive, the predicted tool life is essential for this efficient production planning. And it allows us to know when a tool is likely to fail and enabling some proactive control. So the key problems associated include some increased machine costs due to downtime, higher labor costs, and unexpected repairs, and some escalated tool costs for frequent replacements. So just to show you guys some cases that demonstrate the advantages of using this controlled environment and predictive maintenance. Here on the left, we can see a medium-sized toolmaker, and with a break-even applying this predictive maintenance methods of 22 months, and from that on, it's reduction of costs. And on the right, we can see a small-sized coolant producer that in just 14 months had the break-even and a lot of cost reduction after that. Lastly, on this section, I wanted to show a good argument for the oneAPI in this special situation. So implementing here the cross architecture development brings some benefits specifically in this case, and here's where it all comes down to, because by writing code that runs on different XPU architectures here, like CPU, GPU, FPGA, microcontrollers, we can optimize the performance and the flexibility for the different scenarios for each client and the industry. And this approach allows us to run our applications on existing computing resources that clients already on. So reducing also the need for additional hardware investments and more. It also enables some adaptations to specific scenarios by selecting the most suitable computing resources for each task. So whether leveraging the parallel processing power of GPUs for intensive computations, or the energy efficiency of microcontrollers. Here we have a broad range of algorithms to apply the predictive maintenance in the industry. And it's good to have the oneAPI feasibility of cross architecture to deal with this range of devices. As we reach into this final section of the talk that I've separated. Here I wanted to do some implementation walkthrough session, but I had some little issues on setting the environments on a specific device here, and then because of for this reason I've separated a application of which is pretty close to what I've put here. It is comparable to the toolware assessment, because in the toolware assessment we basically run algorithms of image segmentation. We create a mask for the wear, and we assess that with algorithms of geometric analysis to measure stats like the VB max and so on. For this, I wanted to find a comparable algorithm or comparable problem, and not sharing some NDA products that I had here on our back. So I found a problem which is pretty popular, the handwriting recognition, digits recognition. I wanted to approach that with you. So before that, I had a list of the algorithms optimized by oneAPI for CPU and GPU. So here I'm focusing just on the scikit-learn, oneAPI for scikit-learn, that provides some optimized implementations of those algorithms. On CPUs, for instance, it accelerates some key tasks such as we see here, the classification, regression, clustering, dimensionally reduction, and nearest neighbors using algorithms like SVC, random forest, k-means, and PCA. And GPUs, it optimizes algorithms in the same categories as well. What we are going to use for this example here is the SVC. It's an SVM, but it is in more specifically an SVC, because we are going to do classifications of the handwritten digits. Yeah, going to the implementation itself, the first step is the importing and organizing data. So first we import the essential libraries here. So we're going to use NumPy for numerical operations, Matplotlib for plotting the images after on, and joblib for saving and loading models. And we're going to take random library for generating the random samples for the trainings. And now the special part here is of this is to use the Intel extension for scikit-learn, and by importing the patch sklearn from sklearnx and calling the patch sklearn function, we dynamically patch the scikit-learn estimators. And this means that under the hood, scikit-learn functions will now leverage oneAPI data analytics library, which is the OneDAL that was already mentioned in one of the talks here before. So it's going to leverage the OneDAL for computations. So why is this so important? So the OneDAL is now providing the optimized algorithms that are highly efficient on different XPU architectures. And we get the accelerated performance here without the changing our existing scikit-learn code base. So we're going to keep with what is familiar to us in the scikit-learn. Once we go to the next step, next we prepare our data. So we load the handwritten digits dataset from scikit-learn's built-in datasets. So this dataset contains, in this case, I think it is 1,800 images of digits, and each one of them with 8x8 pixel matrix. So it is a 64 features per image of this 1,800 data set. And next we prepare our data. So we have the features, index, and flatnet pixel values from the images in a vector. For the labels, we have the actual digit values corresponding to each image. So we split the data set into training and testing, and set using an 8-20 rule here split, ensuring that the model can be evaluated with our unseen data. So to enhance the model performance, we normalize the features using max absolute scale, and this is especially for the SVM scenario. This scales each feature to be within -1 to a max of 1, which is really beneficial for the SVM because it's sometimes sensitive to feature scaling. So the next thing is to train our model. So now we proceed to initialize the SVC from scikit-learn with specific hyperparameters. So here we are setting gamma to 0.001, controlling the influence range of a single training example. This is set to this value on average because we are trying to avoid some overfitting scenarios here, results. We are setting C, which is the regularization factor, to 100. So balancing some also misclassification because in one hand we are avoiding the overfitting with gamma, but here we are setting a high value for C. To avoid this misclassification of the training examples against the simplicity of the decision surface. So yeah, now thanks to our earlier patch called, this SVC model now uses one DAO under the hood, and training process leverages the optimized algorithm. So it results in a faster computation time and significant advantage in the industry applications where time is critical, not especially in the training scenario, but more in the inference that we are also going to see later, some metrics for this. Yeah, then we trained the model using the model.fit function. And after we train, we save the file using the joblib dump function. So going for predicting the results, we load our saved model using the joblib now load function, and using the loaded model predict function, we make the predictions on our test data set. And now due to the optimizations, it's a big faster inference times, and really beneficial for the industrial scenario. So the result is this Y pred vector is an array of predictive digit labels, and these predictions will help us to evaluate our model's performance and its potential applicability in real-world scenarios. So now in step 5, we want to visualize the predictions we did. So now we bring our results to life. We randomly select 6 images from our test set to visualize using here matplotlib, and we display each image alongside with its predictive label. And this step serves for some purposes as like validation. So we quickly assess if the predictions seems accurate. We generate some insights to understand where the model is might be making some mistakes, and we create visually we convey results to stakeholders who may not be technically inclined. But for the next step, where we are evaluating the model, we are now more in the technical metrics. So we randomly select also 6 images here in the example. We use matplotlib to display, and we assess if the prediction seems accurate using some metrics as the accuracy to also visually also numerically convey the technically inclined stakeholders. So finally, for our last step, we are going to export the results, and now we save the predictions into an CSV file using NumPy save text. And this the CSV decision here is to simplify, ensuring the compatibility and ease of use across the various tools commonly used in the industry. So yeah, then we conclude here in our last line of code with a print statement confirming the successful completion. So I've brought also a comparison case here to see the patched and unpatched version of a support vector classifier, the same algorithm that we used. And we observe a significant difference because in this test, we're using 20,000 samples with 30 features, and the unpatched SVC algorithm completed the task in more than 30 seconds, as we see in the graph. Whereas when we applied the oneDAO patched version, it has achieved an impressive 12.3 times its speed up. So this could mean that, especially in this situation, this can mean that computations which previously took over an hour can now be completed in minutes using this type of scenario. So in essence, by seamlessly integrating oneAPI, in this case, oneDAO into our existing scikit-learn workflows, we unlock substantial performance gains without the need to rewrite our code to different architecture devices. And this efficiency empowers us to handle larger data sets in less time and more complex models with ease. So yeah, that covers all the topics that I wanted to bring here and share. So now, as a final conclusion and bringing the key takeaways, I really wanted to bring this application scenario of the predictive maintenance that I've been dealing with for the last years. Because for me, it really makes a lot of sense what oneAPI is trying to solve and bring to the table. Because especially for writing the same code base and operating in different devices, it was a really big takeaway for us. So we have seen a lot of benefits in our process of development. And if you guys want to get some resources for further learning on this topic, I've listed some of the links that you can get to learn more and get and also read some documentations that I've put here on the scikit-learn library. And I wanted to leave here also my contact details if you want to reach out. There's here my email, my LinkedIn, and also my website that you can find me on those.